Hello, everyone. In today's lecture, I will talk about long short-term memory network for earth science. My name is Yao Zhang, and I'm an assistant professor at Peking University. This lecture will include the following sections. We will first introduce machine learning, especially the neural networks. We will also briefly talk about the recurrent neural network. Then we will go through the long short-term memory network, the LSTM. We will introduce the structure of LSTM, how it works, some other forms of the model, and why do we need LSTM. Lastly, we will briefly talk about some application examples. There will be an exercise, but we will not cover it in this lecture. I suppose most of you have already heard of the machine learning before. It is quite different from traditional programming. In the traditional programming, we have the data and we have the program or a model, which is developed based on prior knowledge. We put them into the computer and it will give us some output. For machine learning, it is different. We have the data, we have the output, we give them to the computer and let the computer generate a program. With this program and some new data, we can use the computer for the predictions. This is similar to a learning process, and that's why we call this machine learning. We obtain knowledge from observations. It is natural that human can do this because we have brain and we can think. We know our brain is made of neurons, billions of them. A neuron can receive signal from dendrites, which connects to other neurons. It processes these signals and then pass it to other neurons through the axon terminals. During a learning process, the connections between neurons can be reinforced through biochemical feedbacks, such that certain neurons are more strongly connected together. When one of them is activated, so will the others. This is the basic mechanism that we can memorize or learn. Computer actually can mimic this process very nicely. The simplest new unit is called a perceptron. A perceptron has multiple inputs, which is like the dendrites of the neuron. These inputs are given different weights and summed together, like how the neuron processes the electrical signal. When the signals passed through a threshold for a biological neuron, the neuron is activated and the signal is passed to other neurons through the axon terminal. In the perceptron, we also have this mechanism. The weighted sum is of the input will be passed to the activation function, sometimes a value, sometimes a sigmoid to mimic the activation of the biological neurons. The value is called rectified linear unit. It's a piecewise function. When the x is greater than 0, y equals to x. When the x is below 0, y equals to 0. Using a mathematical language, we can write it this way. It is the weighted sum of the input, and then we apply an activation function to it to get the output. To help you better understand the machine learning, we will use an example here. Let's say we would like to predict the plant photosynthesis of the gross primary productivity, GPP, based on climate variables. We all know that plant photosynthesis happens when plants absorb light and fix CO2 to make carbohydrates. There are several factors to consider during this process. For example, climate conditions that directly affect the speed of the reaction. This include radiation, temperature, water in the soil and in the atmosphere, VPD. In addition, the plant conditions, for example, the leaf amount, the nutrients, also have an effect. We can build a very simple multivariate linear regression model, which includes the variables we just mentioned, the x1, x2, x3, x4. And Each of the variables will give a coefficient, the A1, A2, A3, A4, etc. Like the equation we show here. We can also write it in a different form. Perhaps you have noticed this is very similar to the perceptron we have introduced before. The only difference that is the perceptron has an additional nonlinear response, which is the activation function. This seems to be very minor difference and should not change the results greatly. However, just like the Philip Anderson said in 1972, more is different. If we combine multiple perceptrons and stack them together to create a multi-layer structure, this becomes a very powerful tool in machine learning. We call it neural networks. For example, here is one perceptron with 3 inputs. And here is another one with 4 inputs. One important feature of neural network is that if you have enough neurons and enough layers, here we have 2 layers, hidden layers, it can mimic any functions. This has been proved mathematically. And this type of machine learning model is relatively easy to train. However, some of the disadvantages are that this is still a black box model, which means the relationship between the inputs and the outputs is not very easy to interpret. Nevertheless, we can observe all variables that may affect the plant photosynthesis with the neural network. We can theoretically very well predict the GPP. However, in the real world, we cannot observe all variables. Some variables are less observed than the others. For example, across the globe, we have hundreds of thousands of weather stations that can provide observations of basic climate variables such as radiation, temperature, humidity, and sometimes VPD. But the soil moisture is only observed at less than 3,000 sites across the globe. There are less sites with in situ observations of plant status. However, soil water and plant conditions are also affected by climate conditions. That means they can be predicted by the climate variables in the past. For example, soil water is affected by precipitation, evapotranspiration, soil characteristics. Evapotranspiration is a function of radiation, temperature, etc. And the plant is also affected by phenology, growth, both of which are affected by biome types, climates, locations. So one solution is that in order to predict the current GPP, we need to use not only the concurrent climate at time t, but also climates from the previous time steps, for example, the t-1 and t-2. Another approach is to allow the information to flow from one time step to the next time step, so that a neural network can memorize and memorize information from the previous state. For example, in this first time step, we will use climate variables and a neural network to predict the GPP. And the GPP in the second time step will be used. In the second time step, the GPP from the first time step will be used as an input variable. And together with other climate variables, we can predict the GPP at the second time step. Similarly, this GPP will be used as the input for the third time step. The assumption is that the GPP at each time step contains the information about LAI, soil moisture, and some latent information, which can flow across time, improving the model performance for the time series data predictions. In a simplified form, we can write the model this way. The model output from the previous time step will be concatenated with the input from the current time step. We call this type of model a recurrent neural network. It is very important for time series data analysis. It should be noted that we just have one model. It is reused at every time step. However, I also have some limitations. One of the most important is that the memory is shorter. After each time step, it may change greatly. For example, in our task of modeling GPP, we hope that GPP carries some very slow varying information such as soil moisture and LAI, but in reality, GPP may not correctly represent this information since it is affected by other climate factors. This will cause, for example, at time step 1, the radiation is low due to the cloud condition, let's say. This will cause a low GPP. And this low GPP will be passed to the next time step. Although the soil moisture and LI may be both high, the low GPP may make the models think that the LAI or soil moisture is low. So that's after several time steps, the information on LAI and soil moisture will diminish, and this memory doesn't work anymore. In fact, for our problem, it is better to separate the fast changing information, for example, GPP, and the slow varying information, such as soil moisture and LAI. For the slowly varying information, we need to update it only when it is necessary so that the information may last longer. This brings us to the key of this lecture, the long short-term memory network. The LSTM is much more complex than a recurrent neural network. The most obvious difference is that there's 2 lines of information passes through time steps. One is similar as the hidden state. The other is called a cell state. This cell state represents long-term memory. For example, the LAI or the soil moisture in our GPP prediction example. Another unique structure of the LSTM is the gate, which determines how the cell status will be changed at each time step. In each cell, the cell state is modified by the gate here and here, and the result is passed to the next step. There are 3 types of gates for an LSTM cell. The first gate is the forget gate. The forget gate is a linear combination of hidden states from previous time step and the input variable for the current time step. We use a sigmoid activation function for this, for linear combination of these 2. The sigmoid makes the outputs in a range between 0 and 1, which means how much the cell state is expected to forget. For example, the forget gate may determine whether it is the end of the season and reset the vegetation information. The second gate is the input gate, which controls the information to be written to the cell. Similarly, it is also a linear combination of the hidden states and the inputs with the sigmoid activation function here. In addition to this gate, we also need the information to be written to the cell. It is called the input content. Here it is the weighted summation of the hidden states of the previous time step and the input for the current time step. So we use the 10H function here so that the results will be in the range between -1 and +1. In our example, the input content and the input gate may determine the carbon input from the GPP to the leaf pool, allowing a dynamic modeling of the LAI. The cell state is determined by the previous cell states, the forget gates, and the new input. So it is represented in this mathematical function. The output gate controls what part of the cell is output to the hidden state. A cell state is passed through a 10H function and then modulated by the output gate. The output gate similarly is a linear combination of hidden state of the previous time step and the input for the current time step, and then with an sigmoid activation function so that the output is between 0 and 1. The hidden state is a 10H function of the cell state times the output gate. This represents that with the updated cell states, for example, LAI, the model will predict a new estimate of GPP for current time step. With this information, we can better understand how the LSTM works. Long-term cell states may be considered as the leaf carbon pool. The short-term hidden states may be considered as GPP, while the input climate variables and the hidden states from the previous time step, we can predict forget gate, which represents the respiratory carbon loss. With inputs from these inputs will also be used to predict a photosynthetic carbon gain and an additional allocation coefficient, which determines how much carbon will be allocated to the leaf pool. The cell states will be updated based on this respiratory carbon loss and the new carbon gain. With this updated cell state, we can predict a potential maximum GPP. And the inputs variables and the hidden states will also be used to get output gates, which represents the environmental limitation on the maximum carbon GPP, so that this tool will be used to predict the actual GPP as the new hidden states. With this updated cell states and the new hidden states, this tool will be passed to the next time step for the new prediction. Please note that this is only what we assume the model will do. But does the model really represent this information during the training? We don't know. This is a comparison between the LSTM and the neural network. We use 13 years of training data and 1 year for validation. The model performance is much better for the LSTM with an R-square of 0.66 than the neural network. The R-square is only 0.4. The results from the neural network shows very large variations, indicating that the result is affected by concurrent climate. LSTM, on the other hand, shows a clear growing season and a dormancy season, and the day-to-day variations are smaller, indicating that the LSTM can represent some slow varying process, which is important for the GPP predictions. Next, we are going to talk about some variations of LSTM. Here we will introduce 3 of them. The first one is the bidirectional LSTM. It has 2 LSTM cells combined together with hidden information be transferred forward this way and backward this way. This is important if we want to make full use of the information from the past and from the future to make the predictions. The other type of the LSTM is the GRU, the gated recurrency unit. This figure shows the clear difference between the RNN, the LSTM, and the GRU. Compared to the LSTM, it has only 1 hidden layer with no cell states. Compared to the RNN, it has multiple gates within the cell. So it allows the hidden state to be changed under certain circumstances, so that the information will last longer. The last is the entity-aware LSTM. So the only difference is that the entity-aware LSTM uses a static input for the input gate. So well, for the other dynamic inputs, they are used for all other gates. So the static inputs can be biome types, soil types, and other static information which does not change through time. So the last question we would like to ask is why LSTM? When do we use LSTM? I think first is when you are dealing with some time series analysis or the sequential data modeling. This is a prerequisite for the LSTM. Second is that if you want to do some modeling, which current states depend on the past states, so there's some latent information. And then there are other situations that if a model that have some hidden states that you cannot directly observe, so you can use LSTM to set it as a hidden states and then to make predictions. Last is that if you want to fill some observation gaps, you can also use LSTM. We will have an example later. So lastly, we will introduce some examples, application examples from the previous studies, so that you will know what LSTM really do in the research. The first example is that the LSTM is used to predict global soil moisture based on satellites and other observations. This is a very similar model that's as we presented for the GPP prediction, but it uses the entity-aware LSTM that considers spatial static information such as land cover types, soil types, both of which are very important for the soil moisture model. The trained LSTM is used to generate a global continuous soil moisture dataset, which show very good performance. The second example is the remote sensing application of generating high spatial resolution, spatially continuous leaf area index datasets. Since LAI variation is low and there may be gaps in the satellite observations, using a bidirectional LSTM can improve the LAI predictions. In this right side figure, we will show that the red line shows the new LAI datasets. It shows the much better seasonal dynamic compared to other datasets. The last example is a study recently published in Nature on precipitation nowcasting. Precipitation nowcasting means to predict future precipitation for a short period of time, usually several hours or one day in advance. This is rather complex deep learning algorithm that's used in this study. It is based on a generative adversarial network, or GAN. GAN is another type of machine learning algorithm which has a generator and a discriminator, and two discriminators here in this study. It is like a compact between these two players, which the generator generates some samples, and the discriminator tries to determine whether it is real or fake. The trained network will be able to generate some samples from nowhere that looks like real data. The gated recurrent neural network, the GRU, is used as a generator which provides the estimate of precipitation in the near future. And two discriminators are used for this temporal information and spatial information identification. The right side of the shows the nowcasting precipitation, which is observed and predicted by the model. This algorithm predicts very high consistency with observations, much better than other algorithms. As you can see in these examples, LSTM has broad applications for the earth science. However, currently in ecology, the application is still very limited. I believe there's a large potential in the field of ecology or the land surface modeling. That is all for today's lecture. I hope you find it useful. If you have any questions, please feel free to contact me. There is also an exercise at the end of the lecture. You may try it yourself. Thank you for your time.